is added with a uh, is now is added, that is you see here p dash equal to p plus t, that is we added our translation factor to the previous position x and y to form a new form x dash and y dash. So if p is your initial position and p dash is your new position, the p dash is obtained by adding p plus t, where p is the initial position xy and what is t? That t is the matrix which contains your translation factor tx and ty. So p dash equal to p plus t. Okay. So translation move the object without deformation, that is rigid body transformation we have already discussed. And besides that, we can know that if we want to change the position of a line segment, you have to only apply the transformation to endpoint. And similarly, if you want to move a polygon from one position to another position, apply the transformation equation to coordinate of each vertex. You need not to apply the transformation to each and every point of an polygon. You have to only apply the transformation to the vertex. If in a hexagon, you have to apply the transformation equation only this 6 point only. So the polygon using the new set of vertex coordinate. Then rotation, we have already discussed in the previous class. This is rotation, and we need three things here: rotation axis, rotation angle, and rotation point, or sometimes it is known as the pivot point. This pivot point may be your origin 0 0 or any other point. Let it xr and yr. So we need these three component to perform the rotation of an object. So if the angle of theta is positive, then the rotation is counterclockwise or anti-clockwise. If the theta is negative, it is a clockwise rotation. So the sign of theta determines the direction of the rotation, and this is your matrix of rotation matrix. And you see here p dash is obtained by r dot p, that is r with multiplied with p. R is the rotation matrix and p is the initial position, that is cos theta minus sin theta minus cos theta. And if here theta is you know that that is here is multiplied r dot p. And similarly, if we rotate with pivot point other than origin, the previous equation was the rotation about the point with respect to the point origin. So if you want to rotate a object in any other point with other than the origin, this equation is used. Similarly, uh, a line is rotated by applying the rotation formula to the each of the end point and then redraw the point exactly like translation. And a polygon is rotated by applying the rotation formula to each of the vertices and redrawing the polygon using the new vertex coordinate. So it is your same is used in translation. And this side is not required. It is a C program uh, to rotate a polygon. So this is not required you, so you can ignore this slide. Then start a new transformation. The third one is scaling. And as you know, the translation is used to change the position. The rotation is used to change the orientation of an object. But scaling is used to alter, change the size of an object. If you want to change the size of the object, either you want to increase the size of the object or diminish or decrease the size of the object, we need to apply scaling. So simple
Sir,
2D
does
scaling.
it change the property of the image as well? The body, the object. When you scale, the property associated with it should also change, right?
The size will change. The
Size will
size will
change,
change.
sir. But what about the intrinsic property, like those in the image? Do we have to enhance the image, or the image quality will remain the same in case
Now
of an
all
image?
now it is rigid body. No other property will not change. The other
Okay.
property is not because it is rigid body transformation. So other property not change. Only the size will be decreased. Size will be either decrease or increase.
Okay, sir.
The scaling is used to alter the size of an object. Simple 2D scaling is performed by multiplying object position x, y by scaling factor. You remember the translation factors is there tx and ty, and here the scaling factor is sx and sy. But here instead of adding, you have to multiply x with sx to get h dash new position. Similarly, y is multiplied with xy. Sy there it is mistakenly written as sx. The second equation y dash equal to y dot sy. I think it is written mistakenly as x. So the second one is y dot sy, that is scaling factor about y axis, and sx stands for the scaling factor about x axis. You see here the x dash and y dash is formed sx0 0 xy dot xy, and your first matrix with the scaling factor matrix and dot xy. If we multiply these two matrix, you see it is same as x dash equal to x dot sx. You see here, if we multiply that ss into x, then 0 into y. So a dash equal to x into sx. Similarly, if we multiply the second one, that is the second row and first column, second row of the first matrix and the first column is the second matrix. So it is 0 into x into sy into y equal to y dash. That is, if we multiply these two equation, two matrix, which is right side of the equation, so you will get x dash equal to s dot sx and y dash equal to y dot sy. So here P dash equal to S into P. S is nothing but that is the element, it contains the scaling factors, and P is the initial position and P dash is the new position after scaling. After scaling, you see here. You see there is an image in the left corner, that is there is a size. After scaling, you see the size is diminished. So it depends upon the size, either is enhanced or diminished, depend upon the value of sx or sy. You see here, any positive value can be used as scaling factor. The value less than 1 reduce the size of the object. If the value you cannot take the negative values, but unlike your rotation, you can take the theta is negative or theta is positive. But here the scaling factor value can't be negative. You can take any positive values. So the values which is less than 1 reduce the size of the object. That is, if sx is a less than 1, so if we multiply that thing, it will be reduced. That is, you know that 50 into 1 by 2, which is 1 by 2 is less than 1, so you get 25. So the value which is less than 50. Similarly, values greater than 1 enlarge the object, and if scaling factor is 1, the object stayed unchanged. The size will not change. The size remain exactly unchanged. So if xs and xy are equal, suppose xs is equal to 2 and sy is 2, this is called uniform scaling. That is, we are increasing the size in order to x-axis and y-axis uniformly. So if the scaling factor less than 1, then the object moves closer to the origin, obviously. So if it is decreases, so decreases, that is the object move closer to the object. If scaling factor greater than 1, then position decreases. If position decreases, it is the object moves further from the origin. You see here, there is a line x So uh, the size is, you see there's arrow. After scaling, you will get a small object, a small line as compared to the original line. But you see which one the closer is to the origin. That is, the size is diminishes here, the size is decreases here. If size decreases means the scaling factor less than 1. So if the scaling factor less than 1, you see the object comes or moves closer to the origin. So we can also control the location of the scaled object by choosing a position called fixed point other than the origin. If it is xf and yf, suppose we want to change the object with respect to another point, another fixed point. So here x dash equal to x minus sf into sx and y dash equal to y minus yf into sy. So new position is this, and x dash and x into xs, xf 1 minus sx, and y dash equal to y into sy, yf into 1 minus sy. So polygons are scaled by applying the above formula to each vertex. Then regenerate the polygon using the transform vertices. Similarly, your polygon can be uh, um, scaled by using the same formula and applied to each vertex. So here is scaling uh, is with respect to any other fixed point other than origin, like your rotation. So we have discussed translation, rotation, and now scaling. We have also two other transformation. One is your reflection and shearing. We'll discuss about that. But before that, let us discuss what is matrix representation and homogeneous coordinate. Many graphics application involve sequence of geometric transformation, which is known as composite transformation. That is, at a time we can use more than one transformation method to a single object. So many graphics application involve sequence of geometric transformation. Sequence of geometric transformation one by one. First translation, then scaling, then rotation, then shearing. So that is known as composite transformation. So like your animations, if you want to animation, you have to apply composite transformation at a time. Design and picture construction application. So we will now consider matrix representation of this operation. So the sequence of transformation may be efficiently processed using matrices. So if you with the matrices, uh, so your composite transformation will be easier and it is easy to calculate and easy to represent. Uh, you see, in previous class, sorry, in previous section, we use a scaling matrix, rotation matrix, translation matrix. So that is the matrix representation. But those coordinates are not homogeneous. Let us see what is homogeneous. The homogeneous, you see, so you see here, here the P dash, the new position is improved by M1 into P plus M2. P and P dash are column vectors. M1 is a 2 by 2 array containing multiplicative factors. We'll discuss about that. M2 is also a two-element column matrix containing translation terms. For translation, M1 is the identity matrix. For rotation of scaling, M2 contains the translation term associated with the pivot point or scaling fixed point. That is M1 is one type of transformation. M2 is another type of transformation. I want to use both in a single on P. And the formula is for this is P dash equal to M1 dot P plus M2. So if you want to apply a sequence of operation of an object such as scaling followed by rotation or then translation, that is, you see, on same body, on same object, we want to apply a sequence of operation. That is, first suppose we have to make scaling, then rotation, and again then translation. So we could calculate the transfer coordinate one step at a time. You need not to calculate one by one. First scaling, then calculate what is the scaling value, then make rotation and get the output, and then translation. No, we would calculate the transformation coordinate one step at a time. A more efficient approach is to combine transformations without calculating the intermediate coordinate values. We need not to calculate the intermediate values. We have to approach a combined transformation. Multiplicative and translation term for a 2D geometric transformation can be combined into a single matrix if we expand the representation to 3 by 3 matrices. Please recall, when we represent a scaling or a rotation or a translation, we had a 2 by 2 matrix. Those matrix is order 2. But in homogeneous coordinate, to perform this type of operation, it is easier to perform those operation, that is your composite transformation, if we expand the representation by a 3 by 3 matrix, 3 cross 3 matrix. Let us see how. We can use the third column for translation terms, and all transformation equation can be expressed as matrix multiplication. Expand each 2D coordinate to the 3 element representation SH, YS and H called homogeneous coordinate. If we expand a 2D coordinate XY to 3 element representation, that is SH, YH and H, is called homogeneous coordinate. And H is the homogeneous parameter such that X is S by H and Y is equal to YH by H. Infinite homogeneous representation for a point. So a convenient choice is to choose H equal to 1. If you take H equal to 1, so X become SH and Y become YH. You see here. The same matrix we used to use as translation matrix, which was a 2 order 2. The matrix was order 2, but now the same translation matrix here, that is same is P dash equal to P into T into P. But here we see we multiplied. If we multiply, you see 1 into X, 0 into Y, Tx into 1. That is S dash become X plus Tx. And second equation, Y dash equal to 0 into X, 0, plus 1 into Y, Y, plus Ty into 1. That means Y dash become Y plus ty. And now I am added a new row. If you multiply that, you will get same. That is 0 into x, 0 into y, 1 into 1. That is 1 equal to 1. That is, we are expanding the translation matrix, which was in 2D, two dimension, now to 3D, three dimensional. XH, YH, and H. XH is here X dash, YH is here Y dash, and H is here 1. So this is a matrix representation of translation matrix in homogeneous coordinate. You see, same matrix representation of homogeneous coordinate of rotation matrix. S dash y dash y dash. It's the same thing you are also in a rotation where you see when we where is the rotation matrix? Which slide? Yes, this slide. You see, this is a rotation matrix. It is you compare this matrix with that matrix. It only contain uh, two rows and two columns. It is a matrix of order 2, 2 cross 2. And here if we multiply, that is you will get the same result. The same can be expanded into a matrix of order 3, 3 cross 3. The same, you will get the same result, but that is the representation of in homogeneous coordinate. What is that? This one. You see the same component are there, s dash is there, cos theta is there, minus sin theta is there, sin theta is there, cos theta is there, but we have added with extra row and extra column, third row and third column. Similarly, to match it, we have to add s dash, y dash and 1. H is 1 here. If we multiply this, you will get the same formula. Cos theta into x, that is x cos theta, minus y sin theta, x dash is equal to cos theta, x cos theta minus y sin theta. Similarly, in the second row is multiplied with the first column, that is sin theta into x, s sin theta plus y cos theta, and 0 into 1, 0. So if we multiply these two matrix, which was in the right side of the equation, you will get the same equation we have discussed earlier. So here you see P dash equal to R into P. Within bracket it is written theta, means that is the it is expressed in the angle theta, so that is theta. You may not write here, you have write only P dash equal to R dot P. So this is your same matrix, but we are able to represent it in homogeneous coordinate, because the homogeneous coordinate is basically needed if we perform the composite transformation and calculate the value at a single go. So you use it homogeneous coordinate. Similarly, the scaling matrix. If you see the scaling matrix in previous slide, you will get a 2 cross 2 matrix. But it is a 3 cross 3 matrix. You see, I have added a extra row and extra column. The last row and last column. So here if we see s dash equal to x into sx, y is 0 and 0. So s dash equal to x into ss. The formula you know. S dash is calculated by multiplying x with ss. Similarly, if we multiply the two matrix, which is right side of the equation, you will get the same. S dash equal to ss into x. Similarly, y dash equal to, you see, we multiply this 0 into x, x into y, and 0 into 1. So y dash become y dot sy, and last one is become your 1 into 1 equal to 1. So same, you will get the same result, but here you see how I represent the scaling matrix which was in 2D, two dimensional, or a matrix of order 2. Here I represent the same thing in matrix of order 3, that is xh, yh, and h equal to 1. And the same formula is used, p dash equal to s dot p, that is s into p. If we multiply two matrices s and p form, you will get the new position s dash and y dash. So this is the representation of scaling matrix, rotation matrix, and translation matrix in homogeneous coordinates. Inverse transformations. As the name suggests, inverse transformation, that is, after transformation, you will perform the inverse transformation, you will get the original object. You see your 2D inverse translation matrix, and it is T inverse. So suppose you already applied a translation operation to an object, it is already changed its position. You know that translation is used to change the location of an object, and if you apply the translation operation, one object has already changed its location. Suppose you want to retain or back the position of that matrix, or sorry, position of that object. So you use inverse translation matrix, where T inverse equal to 1 0 minus Tx, 0 1 minus Ty, and 0 0 1. It is different. This matrix is different, a transformation matrix. It is exactly was opposite of translation matrix. So obviously, if we multiply T inverse into T, we get I, the identity matrix. T is a translation matrix. T inverse the inverse matrix. Then we get I. I stands for here the identity matrix. Identity matrix means the matrix which all the diagonal element, main diagonal element are 1, and all other element are 0. You know that is if a matrix which is having element 1 at as its main diagram, or other elements are 0. So you will get I. I means that is there is no change of the object. So the inverse translation matrix is uh, used to retain the original position of the object after translation. Similarly, this is inverse transformation of rotation matrix. You see, these matrices are different. Cos theta, sin theta 0. And you recall that is a sin theta minus cos theta, sin theta, cos theta. But here is cos theta, sin theta 0. Here is minus. In second row, there is minus sign, minus sin theta, cos theta 0, and then 0 0 1 0 0 1 for the homogeneous coordinate. And R inverse are opposite to each other. That is, if you want to rotate, if you already rotate the object, and then you want to again uh, again retain the same position or original position, you have to rotate the object again. You have to apply the inverse rotation matrix, inverse rotation operation. So the inverse rotation matrix is here, and also R inverse into R also gives your identity matrix, because you know that if A is a matrix and A inverse is inverse matrix, so A dot inverse, that is a multiplication A and A inverse, gives you a unity matrix. So here R inverse into R is I. So the rotation matrix, inverse rotation matrix, is used to retain its original position before rotating. So 2D inverse rotation matrix, if theta is negative, then it is clockwise. So it is opposite. So in R inverse into R equal to I. You know that to a matrix when it is multiplied with its inverse, you will get I, an identity matrix or unit matrix. Only sine function is affected. You see here in previous slide, the cos theta is there. Only sine theta are affected. That is, in rotation matrix, it was cos theta minus sine theta. Okay, then sine theta, cos theta minus sine theta, cos theta. But here, cos theta, sine theta minus sine theta, then cos theta. That means R inverse equal to only update the sine. The cos theta is as it is. There is no change in like your rotation matrix. That is inverse. If you compare inverse rotation matrix and rotation matrix, the cos theta, the position of the cos theta is already same. Only the sine theta and minus sine theta will be altered. That is, if you take the transpose of the matrix, it will get the inverse. You need not to find out the inverse of the rotation matrix. You only take the transpose, because only sine function is affected. Cos theta, cos function not affected. So if you take the inverse of this, it will become your rotation matrix. It will exactly become a rotation matrix. So you need not to find out the inverse. So that is why. So whenever to calculate the inverse of a rotation matrix, you only take the transpose of the matrix. Transpose means you change rows into column and column into rows into change, and vice versa. So as only sine function is affected, therefore we can say R inverse equal to R transpose, RT. Okay, which I have already discussed. Two D inverse scaling matrix. And the scaling matrix is same as inverse scaling method. The only difference is, in place of Sx is which is multiplied, here Ss is divided. That is, you multiplied 1 by Sx, okay, to get the size of the original object. That you know that applying the scaling matrix or scaling operation, the size is already changed. If the Ss, the factor is greater than 0, size is enlarged, and it is moves away from the origin. And if it is less than 1, the size is diminished and it moves towards the origin. We have already just discussed. So if you apply SS scaling operation, you know that the size is already changed. But suppose you change your mind and you want to again the size, you want to find the original size of the object back. So you apply your inverse scaling matrix, and you see the S inverse equal to 1 by Sx. In place of Sx, you see there is 1 by Sx. and 001 and 0012 rows is added for homogeneous coordinate. And obviously, so if you multiply S inverse and S, you will get a unit matrix. So we have discussed inverse translation matrix, inverse rotation matrix, and inverse scaling matrix. So then 2D composite transformation. 2D composite transformation. So that is, we can set up a sequence of transformation as a composite transformation matrix by calculating the product of the individual transformation. That is, we can apply the sequence of transformation, first scaling, then translation, then rotation in any order, or in a single object. On a single object, we can apply a setup or set up a sequence transformation one by one. Uh, so we can set up a sequence of transformation as a composite transformation matrix by calculating the product of the individual transformations. That is P dash equal to M2, M1 and P, where M1 or M2 are the sequence of transformations. So which is as M dot P or M into P. What is M? M is the product of M2 and M1. Composite 2D translation. If two successive translations are applied to a point P, then the final transform location P dash is calculated as. That is, we want to apply two translation operation to a single object one by one. That is first T1 and then T2. So if two successive translation method, that is you want to change the position from S from P to P dash, then P dash to suppose P double dash. Okay, so this is your this is two successive translation is applied to a single point P. I, you see how P dash equal to Tx2 Ty2 dot Tx1 Ty1 dot P, that is equal to form Tx1 and Tx2 are added, Ty1 and Ty2 added, then dot P. That is two translation matrix are added, two translation factor is added, Tx1 and Tx2. We need to perform the first operation and then second. You can apply only one operation, Tx1 plus Tx2, Ty1 plus 2y2. Suppose Tx2 is 3, Tx1 is 2. Suppose you have done that is Pt5, 3 plus 2, 5. Similarly, for the y coordinate. Are you getting?
Yes, sir.
Yes,
And
sir.
see,
Yes, sir.
you see in the matrix form. You see. So you need not to apply the first matrix first, then get the result and apply the second matrix. No, you only multiply T1 and T2 has two matrix, and the result matrix is 1 0 Tx plus T1x plus T2x. Similarly, T1y plus T2y and the 0 0 0 1 and 1 0 0 is your, you know that is coordinate systems. homogeneous coordinate system. So you can only apply the regional matrix into P and get your P dash. So you may understand that why the need of the homogeneous coordinate for these. That is, we are using here successive translation, composite transformation. No doubt, two translations are there. Two translations are there. We can use also translation followed by scaling, followed by your rotation. We'll see in the next slide. But you see here, two translation method are used, so that we are using this. Similarly, for composite rotation, we dash P dash R theta 1 plus theta 2. Suppose first we have to rotate and suppose you want to rotate an object first 45-degree, then 30-degree. Okay. So first 45-degree, then 30-degree. You have to rotate that angle about 45 plus 50, 75-degree. Suppose you want to rotate an object 45-degree clockwise, 60-degree anti-clockwise. So you can add plus 45 minus 60. Okay, that is you have to rotate only 15-degree. Only 15-degree towards negative. So you need not to rotate the first 45, then 60 to anti-clockwise. No. Okay, you only added the angle and apply that thing. That is, here we used to find P dash using a single operation only. We need not to perform the operation twice. Suppose we have to rotate an object 10 times or 5 times or thrice. So you need not to perform the operation same or 5 times. You only add these theta and then rotate. So this is the benefit of representing rotation matrix in homogeneous coordinate. Otherwise, it will be difficult. If we do not represent a homogeneous coordinate, it will be difficult to represent to perform composite 2D rotation or translation or scaling. You see here. So first applying theta 2, first matrix you see based upon theta 2, cos theta minus sin theta cos theta. Only cos theta is remains same. There will be no change. Only you see sin theta sign is change. So please remember when you represent a rotation matrix, only the sign of sin theta will be changed. The cos theta, you see, there is no cos theta having negative sign. You see here, first cos theta is applied, first matrix for theta 2 is applied, then theta 1. We need not to perform this operation one by one. The first two matrices is then multiplied. So only the theta 1, theta 2 is added. It is cos theta 1 plus theta 2. Only these are theta 1 and theta 2 added. Suppose the cos theta 2 is 40 and cos theta is equal to 30. So 40 plus 30 is added. Theta 1 plus theta 2 becomes 70. So here cos 70 you have to rotate. 70 degree you have to rotate. So this is your composite transformation. Successive two rotations are here. First one is theta 1, then is theta 2. Similarly, scaling. Composites 2D scaling. So first is x2, y2 is there and x1, y1 is there. So you will get s is x1, s2 dot s1, y2. So two scaling factor is multiplied. Okay, suppose you want to change the size thrice and want to diminish the size by half. So you can use a single matrix to perform these two operations. You need not to multiply the first two, then the resultant matrix with the third one. No, you have to only multiply or perform only single operation. You see, if there are two operations with two scaling factor s2x and s2y and x1x and x1y, you need not to perform two operations separately. You have to only perform one operation, which one the resultant matrix s1x into s2x 0 0 0 x1y s2y 0 0 0 1. Okay, suppose the first scaling factor is 3 and then the scaling factor is 2, then the result scaling factor is 3 into 2 6. That is, you want to enlarge the size 6 times. Okay, so this is your composite transformation, composite 2D translation, composite 2D rotation, and now the composite 2D scaling. These are some successive translation and additive. That is, if we successive translation, you have add only. That is, suppose you want to first tx equal to 3 and t1x is equal to 3 and t1 2x equal to 3, then it is 6 times. But if you want to scaling factor is 3 and then scaling factor is 3, then you have to enlarge 9 times. Okay, so your successive translation are additive, whereas successive scaling factor are multiplicative. For example, if you triple size the object twice, so the final size is 9 times original. But if you applying triple of the object of translation object, it will be 3 plus 3 6. So 6 will be added. But here,
What, what about successive this rotation, sir?
rotation is also added. Theta plus
Additive.
theta 1 plus theta 2. Yes, theta 1 plus theta 2. If we want to rotate 45 degree fast, then 30 degree fast. No, then 30 degree. Then the result is 45 plus 30, 75. It is not multiplied. Isn't it?
Yes, sir. But that is the cosine of that angle, no, sir? The cosine of that addition. Okay.
Cosine to remain same. That is the different thing. But the theta are added there.
Yeah, that you can say.
General pivot point rotation. Okay. We had an idea that is we can rotate an object about an origin only. But now we can rotate an object with any other point. We had a formula, but we have at that time we don't have any examples. Let us see how general pivot point rotation. As the name suggests, general pivot point, that is the rotation with respect to any other fixed point other than the origin. It is not origin. You have to rotate that object not with respect to the origin, but respect to any other position. That is called the pivot point rotation. General pivot point rotation.
So that fixed point will be on from the object, sir, or anywhere in the
Anywhere outside
plane?
the object. Anywhere outside the object.
Okay.
Okay. Anything outside the object, and but not the origin. The origin, if the origin is there, we already know. Let us what are the steps? What to do? If we rotate an object with respect to any other pivot point, but not the origin. Okay. First, we have to translate the object so that the pivot point is moved toward the coordinate origin. Okay. First, we have to translate the pivot point to the origin. Okay. We know that how the point is translated.
Yes, sir.
Okay. So we know that once the pivot point come to the origin, it is easy for us to make rotation. So after performing rotation, again take the pivot point to its original position back by using inverse translation. Okay, same thing is written, you see. So once the pivot point is come to the origin, it is for us now not difficult. We know that the rotation about origin. So then rotate the object about the origin, which is simple for us. We know that how to rotate. We have that rotation matrix. We have the formula. So once it's rotated, this is not the original output because we are now rotating about the origin. So again translate that pivot point to its original position by using inverse translation. You see, translate the object so that the pivot point is returned to its original position. That is, it said that indirectly use inverse translation. Are you getting these 3 points?
Yes, sir. Very clear, sir.
That's simple. Let us see how. You see, general pivot point rotation. You see, there is a rotation, there is a pivot point, which is uh, marked as a white point. Is it visible? I want to rotate that object toward that point with respect to that point.
Okay.
Okay, either in clockwise or anti-clockwise, depend upon the sign of the theta. Okay. So first, what to do? First, translate that point to the origin. You see, now I have done in my second picture.
Yes.
I'm only, I did have nothing. I only translated that point to the origin. Okay. So once it's come to origin, now make the rotation. You see, the angle is not specified. Suppose the angle is 90 degree. Now I rotate towards anti-clockwise.
Anti-clockwise.
Yes.
It's positive,
One.
no, sir? Anti-clockwise is positive.
Yes.
Okay.
Now rotated. Any theta,
Sir,
any value.
sir, anti-clockwise is positive or clockwise is negative, like that.
Yes,
Uh-huh.
here in this case.
But
Yes.
clockwise is positive and anti-clock is negative.
No, leave that earlier theory. Here it is different.
Okay. So you see
Okay,
here.
is it, sir?
It is not true, but actually you see, regardless of theta, you think that the rotation is done. You see, I have rotated here. So first what I have done, that is I translating the pivot point to the origin. Once it come the origin, I have rotated that. I don't know what is the value of theta here. Okay, but you assume that it is rotated. And you see, that is theta. So
Then
once it
again, you will
rotated,
have to translate, sir.
again because it is not my output. It is
Yeah, we have
actually
to
this.
translate to
It
the
is not my
original
output.
position.
Yes, you see the output now. Okay, I again translating that point to its original position. What I have used here to get this, what I have used here, did you know? Inverse translation, isn't it? You see, now the body is rotated, the object is rotated about specified theta angle with respect to the pivot point.
Why
With
can't we
respect,
do it without translation, sir?
hmm?
Why can't we do it without translation at the
We
first
don't
step?
have any formula. We don't have any formula about pivot
Okay,
point. We have to
okay,
first come to translate to the original point.
okay,
We don't have any translation matrix.
okay.
Okay, so it is necessary to translate to the origin first. So this is a rotation of an object with respect to any pivot point other than origin. The process is simple. You only translate to here origin. Once it come the origin, it is simple to rotate, and after rotation, never forget to take back to its original position using inverse translation. If we represent the same thing in your matrix form, you see, first one the translation matrix, second one is the rotation matrix, and third one most importantly it is inverse translation matrix. You see minus xr and minus y are there. And if we multiply this, and you will get the resultant matrix by taking xr y and common, and then you do that. So that is here what I have done. First we have to translate, then rotation, then again translate. So I use here three transformation operation one by one. But you need not to perform one by one. That is, you have to only apply the third one, the resultant matrix, to the operation to get that output. Cos theta minus sin theta, and xr 1 minus cos theta, yr sin theta cos theta, yr into 1 minus cos theta minus xr sin theta, then 0 0 1. So this is
This is
the
very complicated, sir.
not complete at all. You
Really?
only simply multiply and take the xr yr common, you will get that matrix. Not complicated. It is you multiply the first two matrix, then the third matrix, and you will get that.
Will any numerical come from this, sir?
Basically not.
Okay.
But this
Thank
is
God.
not actually it is seems looks like complex, but actually it is simple. If you multiply the three matrix, you will get this output. But you have an idea that how the rotation take place with respect to any other fixed point other than the origin. This is the idea.
Any
And
practical application, sir, of this?
uh,
Okay.
suppose when you any particular application means suppose in your Photoshop machine, or where you make your photographs editing.
Canva, sir. Canva में भी
Yeah,
करते
yeah, yes, you are using in that case. That is, you have to change the size. Then it is you have take the position from one to another. Then you rotate it. So all are the composite transformation.
So there are programs written for this, sir. If
Yes,
we have
always
Canva,
program, always program. Software are
okay,
there. Yes, the operator, the in a Photoshop operator does not
Hmm.
know the what it has already tools. The
Yes.
software is already written that. He has pre-prepared tools. It has. You only rotate that. He does not know how what is the coding behind it. The
Must
software
be
is for
very
made for that.
complicated program, sir.
Oh, yes, it is complicated. We had a slide na for in C program.
Yeah, I
Have you
saw,
seen?
sir. Yeah, चक्कर आने लगा, sir.
General fixed point scaling. The same, the same concept, but we have to apply here scaling, fixed point scaling, pivot point scaling. Let's wait 2 minutes. Take some water. Uh, that is here the scaling operation will be done with respect to other point, any fixed point, any pivot point other than origin. The same steps. That is, you have to translate the object so that the fixed point coincide with the coordinate origin. So first we have to change that pivot point, the fixed point, change the location of the fixed point or pivot point to the coordinate origin. Once it comes origin, it is not difficult for us to perform scaling operation. You see, to scale the object about the origin, we have standard matrix to perform that operation. So we don't have any problem now. So again, translate the object so that the pivot point is returned to the original position. Exactly the same steps of previous pivot point rotation. Only here, in place of rotation, we have to perform the scaling operation. Let us see. General fixed point scaling. You see, we have to scale that object with respect to XR and YR. Here is the pivot point. That is, we have to change the size with respect to this point. Okay, first we have to translate that point to the origin. You see, now it is done. So once the pivot point coincide with the origin, we don't have any problem to perform scaling operation. You see, now the scaling operation is done. Xx and xy we have enlarged. So now our work is to return back. That is using inverse translation. Here the scaling is performed in origin. So we have to come back. You see, the fourth one. Now I are able to perform scaling operation with respect to any general fixed point other than the origin. So scaling operation is done with respect to a fixed point. First we have to translation to the origin. After it comes from origin, then we have to perform the scaling operation using the same formula SS and SY and the translation matrix, and again return back by using inverse translation method. Inverse translation method and get the pivot point fix. You see, this is the rotation about the point XR wire. About the point XR wire means that point will not change. You see, the position of XR and YR in the initial position and final position has not changed, remain unchanged exactly. The other points change. The other points change. The other points in that figure change, but that point is not changed. The XR and YR in the first initial position and final position. You see, the figure 1 and figure 4, the position of XR and YR not change, but the sizes of that change. Okay, and other point within that figure within the object changes, but that point, so that is why it is called fixed point scaling. That is scaling with respect to a fixed point. That point will not change its position at all. So I represent it the same thing in matrix form. You see, the first one is the scaling factor. Here xf and yf is written. So it is same as x y tx and ty. It is xf and yf is written. So do not confuse. It is same as tx and ty. So then you see sx 0 0 0 y 0, the second matrix 0 0 1. It is nothing but it is a scaling matrix. So first translate to the origin and then apply the scaling method or scaling matrix you see. And third one you see, it is the inverse translation method to get our pivot point location fixed, its original point, its original location. And if we multiply this thing, you will get the resonant matrix. So your t xf yf into s into minus t, that is inverse translation. That is why the coordinate are minus xf minus yf, and you will get the original matrix sf yf ss sx sy. S is the your original form after scaling. So here also we are able to perform how many operation? 3 operation: translation, scaling, and then inverse translation. That is also one type of composite transformation. So do not forget the benefit of representing it coordinate axis, homogeneous coordinate axis. (2D) composition transformation, general 2D scaling directions. Above scaling parameter we are along x and y axis. So what about the arbitrary direction? So this is x and y axis. Scaling parameter S1 and S2 along orthogonal direction defined by the angular displacement. Angular displacement theta. That is if we so which direction depend upon the theta. Let us see how to the scaling direction. This is the procedure. Rotate so that the direction coincide with x and y axis. That is, if we want to 2D scaling directions. So here the direction must be in x and y axis. That is, we want to direction of another axis S1, S2, and S1 and S2 perform angle inclination angle theta. You see the previous slide. Suppose this is my axis S1 and S2. That is why I want to scaling a factor with respect to not the x axis, y axis, with another axis S1 and S2. That is, you can tell that is another orthogonal direction S1, S2, and you see that the S1 is here. There is an angle theta with x axis. S1 performing angle inclined angle theta. You see. So if we want to make here scaling, we have to first rotate the object, rotate that S1 and S2, that is coincide with x axis and y axis respectively. S1 coincide with x axis and S2 is a coincide with y axis. We have to rotate first, anti-clockwise. Same thing is written here, you see. Rotate so that the direction coincide with x and y axis. Apply scaling transformation now, S1, S2, and rotate back. Okay, that is inverse rotation. So rotate so that the direction coincide with x and y axis. Apply scaling transformation and then rotate back. That means use inverse rotation transformation. So the composite matrix is R inverse, then S into R1, R2, then R theta. So you see here, if you multiply this matrix, you will get a regional matrix like this. This is some matrix concatenation property. That means you tell that if we don't have any homogeneous coordinate system, two matrices can be multiplied. So there may be some cases, you know, that there is a criteria from matrix multiplication. That is matrix multiplication. That is if you multiply the two matrices A and B, the number of columns in matrix A must be equal to the number of rows in matrix B. Okay. So there are some property of matrix multiplication. Once the multiplication done, that is matrix multiplication not commutative. That is A dot B not equal to B into A. That is B into A. That is B or A may not be suitable or comfortable for matrix multiplication. May not be comfortable for matrix multiplication. Suppose A and B are two matrices, and A and B are comfortable for multiplication. A and B can be multiplied, but B, if we multiply BA, BA may not be comfortable for matrix multiplication. And if it is possible, if it is comfortable, you will not get the same result. You may not get the same result. So that is why the matrix multiplication is not commutative. That is M2 into M1 not equal to M1 and M2. But matrix multiplication is associativity. If three matrices M2, M3, M2, M1 are comfortable for multiplication, M3 into M2 into M1, that is, if we multiply first two and then multiply the resultant matrix with M1, you will get the same result if we multiply the second and first and multiply the third. So a composite matrix can be created by multiplying left to right, pre-multiplication, or right to left, post-multiplication. You will get the same result. That is, matrix multiplication is associativity, but it is not commutative. Matrix concurrent property, but two successive rotation, two successive translation, two successive scaling are commutative. You see, this is a interesting thing. sometimes or in which a sequence of transformation is performed may affect the transformed position of an object. That is sequence of transformation. Suppose you make translation then scaling. Is it same first scaling then translation? So here you see may affect. You see here. In A, an object is first translated in x direction, then rotated counterclockwise, anticlockwise through the angle 45 degree. You see. But in B, I reverse the order. The object is first rotated 45 degree counterwise and then translated in the x direction. You find the difference. Okay. Yes, ma'am. Okay. Did you find the difference? That is, they are not same. They are not same at all. You see, the output are different, which are represented in blue color. The final position is here, and the final position of B are different. So sometimes the sequence of transformation which is performed may affect the transformed position object or may affect the output of the object. So so far we have discussed three transformation method: translation, rotation, and scaling. And composite transformation, homogeneous coordinate, and rotation or scaling about a fixed position. Now the fourth one, other 2D transformation, 4.1 reflection. Transformation that produce the mirror image of an object. Mirror object and object, it is called your reflection. If you stand in front of your mirror, you will get of image. The image may be virtual, but you will get an image, a virtual image of you. So here you see, my original position is 1, 2, 3. There is a triangle-like structure, which are 3 vertices and marked as 1, 2, 3. If we put a or keep a image, if we keep an image on x-axis, if we keep an image on x-axis, you will see this image of the original image of the object, which is depended by 1 dash, 2 dash, and 3 dash. That is, you keep here the mirror on x-axis. So this is a reflection about x-axis. This is a reflection about x-axis here. So I can tell I did here the reflection operation about x-axis. Similarly, you imagine if you keep the mirror on y-axis, in which quadrant you get the its reflection image? In second quadrant. In second quadrant. So this is a reflection about y-axis. You see, reflection. So image is generated relative to an axis or a reflection by rotating the object 180 degree about the reflection axis. So this is reflection. That is, if we rotate the object 180 about the reflection axis, so this is called a reflection. So reflection about the line y equal to 0, the x-axis. So if we reflection a object with respect to or about the line y equal to 0 or x-axis or y-axis. So in previous example, it is about x-axis. You see, it is about x-axis. That is the rotation is about x-axis. That is the point line where y equal to 0. You know that all the points on x-axis is 0. You see, this is the reflection matrix about x-axis. 1 0 0, 0 minus 1 0, 0 0 1. Okay. So you have to remember the matrix of all the transformation, translation, reflection, rotation, scaling, 1 0 0, 0 minus 1 0, 0 0 1. This is the matrix, reflection matrix about x-axis. Similarly, you see the same matrix here, the same object is here, which is reflected about y-axis. So you see the original position of an object which is marked as 1, 2, 3, which depends on the dotted line. So if we keep a mirror on a y-axis, so you will get the original position, which is 1 dash, 2 dash, and 3 dash. So this is nothing but this is a reflection of an object about y-axis or the line x equal to 0. Can you write the translation matrix for this? Sorry, the reflection matrix for this. Please write in your copy. Then we will check what is the reflection matrix. Can you guess? So this is a reflection about the line x equal to 0, the y-axis. No doubt we will get a different reflection matrix for a y-axis. You see, in previous one, the centered one, which was in second row and second column, as minus sign, but here you will get a negative sign. You see, in x-axis, so x coordinate changes. So this is a reflection matrix about the y-axis. Reflection about the origin. You see, so first we know that the reflection about x-axis. Then we have done reflection about the y-axis. But here reflection about origin, not y-axis, not x-axis, not x equal to 0 line or y equal to 0 line. It is about 0 0 point. That is the origin point. That is, if you keep a mirror on the origin, you see the reflection changes. You see the original position, which was in dotted line. And after reflection, you will get the position in that position. And to see the the reflection matrix. That is, if you combine those, that is reflection about x-axis and y-axis. In x-axis, the -1 is the center, and it about y-axis, the -1 is the first element. So now the minus sign is in first element as well as the middle element. That is second row and second column. Okay, so here repression about origin. Okay, so we'll discuss in the next class from the next slides. So any queries, any issues?
सर लास्ट क्लास में सर मैं अटेंडेंस डालना सर भूल गया था कल के क्लास में.
अच्छा, तो व्हाट्स योर नेम?
सुमित कुमार सर 2400369825.
Okay. You write your name and number today. So I will.
Sure, sir.
Okay.
Sure, sir. I will write it. I will even write that I missed putting the attendance yesterday. Okay, thank you.
So thank you all. So you can
Sir,
leave now.
we have class from 3 onward, na, today.
Yes. 3 p.m.
Another class. 3 to 5.
3 to 5 today.
Okay.
Thank you, sir.
Okay.
Thank you, sir.
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 Thank you, sir.